for this example, we've got two connected particles, P and Q, with masses 5 kilograms and 3 kilograms respectively. So particle P, this one here, is 5 kilograms, particle Q is 3 kilograms. They're connected by a light inextensible string, so I'm just going to draw that string there. Now, if they are connected by this string, we know that we're going to have some tension in the string. Now, this tension, we're not going to fully understand the direction until we understand what forces are being applied to the string. So we'll come back to that tension in a moment. We're told that particle P is pulled by a horizontal force of 40 newtons along a rough horizontal plane. Rough horizontal plane, that means we must have some friction. So it's being pulled along, we're going to say that it's being pulled along this way, so we're accelerating towards the right by 40 newtons. The next sentence says that particle P experiences a frictional force of 10 newtons, so in the opposite direction to that force that's being pulled by, we've got friction of 10 newtons, and particle Q experiences a frictional force of 6 newtons. Now, if we consider this particle here, it's being pulled to the right, which means that the tension in the string must be going this way. This particle here, it's got a frictional force of going to the left, and it's being pulled by this string, so we must have tension going this direction. So I've drawn my force diagram. The last two forces we must have are our normal contact forces. I'm just going to call the normal contact force for Q R1, and we're going to call this one R2. We've now got to do the weights of each particle. So we've got the weight, remember, is equal to mass times gravity, where G is 9.8 meters per second squared, just a reminder there. So we've got 3G newtons going in the opposite direction to the normal contact force for Q, and 5G newtons going in the opposite direction as the normal contact force for P. So I've drawn my force diagram for the whole system. Part A asks us to find the acceleration of the particles. We're going to resolve horizontally using F equals ma for the whole system. So resolving horizontally for the whole system, our resultant force, we've got 40 newtons going in that right direction, in our positive direction. We're going to subtract the friction force for P, which is 10 newtons, subtract 6 newtons, our friction force for Q. Now we have tension going in the right and tension going in the left. So if we were to add T and subtract T, we'd get 0. So we don't need to include the tension here. And that is equal to mass times acceleration. The total mass, because we're looking at the whole system of the connected particles here, is 8 kilograms. So we've got 8A. So 40 subtract 10 subtract 6, that is 24. So we've got that 8A equals 24, and so A equals 3 meters per second squared. Now for part B, we're asked to find the tension in the string. So for part B, if we resolve horizontally just for one of the particles using F equals ma, we will be including that tension and therefore can calculate the value of the tension of the string. So let's do it for particle P. So for P, if we resolve horizontally, we've got 40 newtons going in that positive direction, and then we've got 10 newtons of friction in the opposite direction, so we're going to subtract 10, and then we're going to subtract our tension in the string, so that's our resultant force, F, that's equal to mass times acceleration. Now the mass is 5 kilograms, the acceleration we just found out in part A is 3. So we've got 30 subtract t is equal to 15, and so t is equal to 15 newtons. For part C, it asks us to explain how the modelling assumptions that the string is light and inextensible have been used. This is a really common question to get in an exam, and every time the answer is going to be really similar. You're just going to have to maybe change the context. So the fact that the string is inextensible, that implies that the acceleration of masses of the particles is the same. So this is looking at our modelling assumptions that we did at the beginning of this unit. The fact that the string is light, this implies that the tension is the same throughout the length of the string, and the mass of the string is negligible, which means we don't need to consider it.